So any force problems, we want to identify the forces acting on the system by doing the free body diagrams, and let's approach it from there. And maybe a little bit of the deal because it's tilted. And did we properly know how to implement this hint? If the car is sliding down, we have a minimum speed, and then therefore, if it's going this way, we know friction is going to go the opposite motion, so it's going to go up the ramp. And then if it's got a maximum speed, then it's sliding up and to increase the radius of curvature, and therefore friction will go down for the same angle. So that allows us to get expressions for the minimum and maximum speed. And then it's like the physics of an engineering problem. So like you can design a ramp now that you know what the minimum maximum speeds are, you know what the angle is going to be, or, you know, like if you, for whatever particular angle, you can design your ramp such that the angle satisfies the speeds that you want, that you already calculated. And then make sure that your surface has comparable static friction coefficient here between tires and road. What kind of asphalt or road surface do you need to pave it with in order to maintain this? You know, so that's the engineering part. And then after you've got the specs from the physicists, go about it. Okay. So let's do that. So this guy is here. It's to tilt. So we have a normal force that is perpendicular. And so all vectors at angles have these two parts. When that happens. Okay, so this is theta. This is the same thing, that's theta. And then we do that. We have the weight always pointing down. This is off axis too. So we have these components like so. Actually, our perspective is this, because X is going to go towards the center of the circle as he rounds the ramp. This will be in sine theta, because opposite the theta. And then this is in cosine theta. So as he's sliding down for the condition of minimum speed, friction is going to go upward. So I'll just do that. And then that's static friction there. This is off axis, so it has components. This is our perspective is this. We have to be aware of that. So that's going to be at some angle like that. And so therefore, this is going to have cosine and sine like that. These thetas are all the same, and this will be Fs cosine theta, and this over here is sine theta. So now we get all the stuff, all the components. And then we know that friction force or static friction force and kinetic is mu s mg. And this is going to be the sine component of that. But I'll make those substitutions later. This is at mg, this is theta. Therefore, you know that this is going to be cosine here. and then that's mg sine theta. All right, so let's get all the forces that act in the x direction and the y direction. All right, so again, our perspective is this guy right here in the bubble. And some other forces. X direction, we have n sine theta minus mus in cosine theta. And those forces are going to be equal to the net force, which is centripetal force, mv squared over r, like ma, where a this time is the centripetal acceleration. It goes in a circle. And then secondly, the forces in the y direction, which is n cosine theta plus mus in sine theta minus mg, no acceleration there. So just again to go back over that, x direction, this is our perspective, everything along x-axis, that's going to be positive. Why do you know? Well, you're going in a circle, how can it be positive? Well, our orientation, our convention is that we're going to put all the forces that point in the direction of the net force as positive. That goes back to chapter 5. It's been our convention from the standard start. So keep that in mind here. In sine theta here, minus mus in cosine theta, that goes away. Remember, fs is mus in. Okay, just expanding it out, cosine theta, mv squared over r. And then likewise in the y direction, we have n cosine theta positive y-axis. And then we have minus mg, and also plus mus n sine theta, positive, positive, negative. And then we take the last equation, y, and factor out the normal force. And of course, 0, and step 4. Any questions so far? See what we did there. Factor out the n's, minus mg equals 0, set them equal. We get an expression for the normal force. Why are we trying to do that? Because ultimately we're trying to get an expression for Vt, but the normal force is in the way. Okay, we're given theta as terms of a variable. We're given mus, okay, those are given. Those are there. But we have to get something for n. And once we do that, then we can get an expression for V. And you do that for the minimum and the maximum, same process. Then after that, you put in your numbers in part B to get your minimum and maximum speeds around the circle. So then, as said earlier, when you have that already calculated, you can go to design the ramp. The civil engineer can come in and make it happen. Okay. Normal force is then mg, not to say the civil engineer won't do it herself, but you know, it's just collaboration. That's my normal force expression. Then now I'm going to substitute that into equation 1. Yeah, and doing it as explicitly as I have it on paper. And so where it was n sine theta, it's now going to become mg over that times sine theta. And it says mu s n cosine theta is going to be mu s, the n expression times cosine theta. So I'm going to do this here and extend down. Because remember, this was my n, and that was my n. And so mu s n cosine theta, n sine theta. You're pretty much ready to go. And you can factor out the mg's. Sine theta minus mu s cosine theta, you know, because that's all mg sine theta minus mu s mg cosine theta. Factor out the mg, and I get this divided by cosine theta plus mu s sine theta equals mv squared over r. And remember, that's the minimum speed. Because the radius is dropped, we have a smaller speed. So that gives you an appreciation, like the cars. Then you can infer, like the cars on the ramp at the bottom are going to be traveling slower than the ones at the top. You see that? Does that make sense? It should make sense. You know, you guys gel with that. I mean, the math works itself out, but you can get appreciation. Sin and Leo and I were talking about, okay, so you're on the inner circle. Well, it's not gonna take you as long. It's not gonna take you as long to go around the circle because the radius is small and the speed is small. So the period of time to get around is smaller. But yeah. Yeah, the logic it takes to get there. Okay, let's hold on a second and go back where you were confused where to start. Like, because that's important. We need to know how to get, oh, this makes sense. So we need to make sure we know how to start. Do you have a specific question on that? Like, how do I get here? This whole VT min business? Or you have a question, but you don't know what question to ask?
Mr. Curry, before we did the normal force was always like mg cosine theta. This time in normal forces equation we also include friction. Like what changed?
Just the orientation of the forces. How many forces and the orientation of the problem. So everything is, because what you're saying there, even though you don't mean to say that, is an absolute statement. We don't do absolutes. Only thing absolutes, well, I say one thing absolute in physics are the constants. But we have to approach every problem skeptically. Like, what's going on here? I know I used to do the cosine theta, but now I got tilts and I got this other conditions. Just take it as it is. That's the conceptual framework, but logically, just the vectors themselves. It's, you know, how they're pointed. And so, I think you're asking in terms of the cosines. Normal force is now off axis. Our orientation is this way. We have a friction. So the orientation plus the friction force changes it. Yeah, that's the sitch. How do you know what steps to start first? Relative to this problem, like I get the drawing diagram. I get drawing the diagram first, but just writing out the equations and equating them. Okay, very important. So here's the drawing. Here's the particle. Here's the surface. You know, by definition, normal force is going to be perpendicular from the surface. And then this normal force being at an angle like this, it's going to have parts. Why? Because definition of vectors having angles, they have two parts, this part and that part. Then you say to yourself, is that which one is X, which one is Y, because they could be different. Here is why you know that X is going to be, this is going to be positive X and not negative X, and that's going to be X period. X, by convention also, always points, positive X always points in the direction of acceleration. In this case, acceleration is this way, to the left, to the center of whatever circle here. This is the pit stop or whatever. That's how you know to set that up that way. Because it always goes back to chapter 5's logic. You get your perspective down. Where are things pointing? Where's the acceleration? Where's the net acceleration pointing? Okay, to the right or to the left. And that's my positive axis in this case. That's my acceleration direction. AC. VT min is tangential, so that's the direction of AC. You got that so far? Because that is very important. Yeah. So AC left, perspective. You know this is going left, so my perspective has got to be this. I know this already. I know my AC, that my perspective must be that. Therefore, when I'm labeling these forces, drawing them out, I can easily then pick out the forces in the positive X direction. In this case, in sine theta. In some other orientation, it could be negative direction, but you want to locate that. Then positive, everything else over here, negative. That's why Fs cosine theta is negative right here. Mu Sn cosine theta is negative, positive, and that's X. Positive X, negative X, nothing else. That equals to the net force. And then Y, positive Y here. Oh, my pen is not marking, or the pointer. Yeah, positive Y, negative Y, and another positive Y. Again, it all just comes from the object as a particle, identify the direction of the acceleration. In this case, to the left, you now have your perspective, draw your forces, all your forces, and you know which ones are going to go positive and negative, X and Y. This is all the battle, really. This setup here, you're pretty much done. Now this is just now icing. So now it's okay, X forces, Y forces. Okay, I'm trying to find V. So we draw the diagram, and since we're not involving kinematics, we write equations for the forces that involve velocity, in this case, mv squared over r to solve it. Yes, mv squared over r is the net force, just like ma back in the day, linear acceleration. This is a centripetal acceleration. So logic is the same. It doesn't involve kinematics, not directly, it involves forces because we have an acceleration. So pretty much that's why it involves forces. And if it's just kinematics, then we don't care about masses and forces and all of that. We don't care about the causes of the forces. We just want to figure out how fast is this going to go in this amount of time. But since we have all these other factors, it's forces. But we can use kinematics to get an expression for how much time it takes to go around the circle, the actual acceleration, and all of that. Okay, so now let's go to step 9. So I want to get expression for V. My masses cancel out on both sides. I multiply both sides by R. I have RG. And that gives me my V min squared, and take the square root. And that's it. And that's my minimum speed. And it's minimum because the radius will be smaller, as I said, as the car slides down. And we show that mathematically. And the same thing works for the maximum case. Now the friction just going to go down, same logic. Now to get the V max for the maximum speed, the car can have without sliding up. I'm just reading my own writing. The friction force will be downhill. So I have this again. Now friction goes that way. Normal force. Again, this is the direction of AC. A sub C. That's positive x-axis then, I know that. So that's going to be positive net force, all that. So this is x, y. And then this time the car is sliding up. If it's sliding up, then friction's got to go down because it's opposite the motion. So I see this is 11, if I may, 12. Once again, kind of the same thing, but this time friction is here. And now I have, let me do an inset, I guess. Friction is like that. Then I have the y component, x component. So this is going to be positive right there. Cosine theta. Let's say this is the This is angle theta here. It's kind of like the same differences. This guy here translating. Okay, so this is be Fs sine, and that'll be negative this time. And of course, mg is also there as well. So we have negative Fs sine theta, negative mg, positive Fs cosine theta. Or mu s n cosine theta. Equals mv squared over r. Then I have n cosine theta positive, and then minus mu s n sine theta, because it's this. So I'm just this, and then a part of that, that's mu s n cosine, or sine, and it's negative, and mg is negative. Know this from our perspective. Frame of reference. And again, why is this theta? Why not this one? Maybe we feel this is going to be that, because conventionally it's all the x-axis. Take the theta from the x-axis. So could we do it also up here geometrically? It doesn't really fit, because we have this right here, alternate interior. So all those are equal. So little things. That's a minus sign. And then you just carry your algebra out same way. On my paper, I had this is part of 12. Equals 0. And equals mg over cosine theta minus mu s sine theta. So everything gets reversed. You know, these terms are reversed. Substitute into equation 1. So you can see it looks the same. It's just the signs are switching. That's equal to the net force. You guys see that? Any questions on that? Make sure you see that. Again, like in the previous case, I made an expression for normal force, and I substituted that back into the original equation. So this is my normal force here, n sine theta, and then mu s n cosine theta. just algebra at this point. Theta mu cosine theta cosine theta minus sine theta. And again, those guys cancel out, and then we have RG that's going to be the maximum, and there you go. Oh yeah, it's bouncing in and out. Okay, and so expressions for V min and V max, and then you just put in your numbers. And so saying you got, or others, so your maximum speed was like 12. It's gonna 5 minutes, I guess we can solve that. So minimum, same thing as the signs are switched there. So we have 100 times 9.8 sine of 10 minus 0.1 cosine of 10. Okay, so you saw that out. What's the minimum speed there? Lack of time. Like 8 point something. I'll just get the expression there, and so you can verify for yourself there. Okay, yeah, 8.573, 8 point something. Of course, same difference. Sine of 10 plus 0.1 cosine of 10 minus 0.1 sine of 10. So the only thing really is the sign switched. I don't know if it's that high. So anybody else get maximum speed, or what are the maximum speeds? So I got one for 200. I think I heard a 12 earlier. But that's what you get. I mean, in the interest of time, we're just going to leave it at that. Because once you get to this point, it's not a big deal. You get off by a number. The most important part is that variable expression, this stuff. So I'll post this up in case you want to go back over it. Again, the logic of this will be similar to the problem tomorrow. 30 minutes of that, and then we'll we'll extract the bits of chapter 13 that we will need going forward. So we won't spend a lot of time on Kepler's laws, all the dynamics. I'll just talk about the first two, and the last one is the most important law that applies to us. And, get to the nitty gritty. Any last questions on that? Yeah, well, let's see if we can clear it up tomorrow. More of that. Okay, so like in 10 minutes, I'll be here, and homework's due at 5. Yeah, my pleasure. Thanks. All right, guys, see you later. Or maybe say some of you at office hours.
Mr. Kelly?
Yeah.
Can you show steps number 13, 14, and 15 again? My internet cut out in the seat.
Steps? Steps 14 and 15?
13 as well.
The steps. Oh, okay. One second. Okay, 13. Here.
Yeah, I'm writing it down right now.
Oh, yeah.
Or maybe I should just take a picture so I won't waste your time.
Yeah. No, it's all right. Not a big deal, because I'm just gonna use this link. Yeah.
Can you show number 15?
Scroll down to 16. I got my headphones.
15. All right, that's it, Mr. Kelly. All right, have a great day. Sorry, Mr. Kelly, I can't hear your voice. Okay, now it's good. Now it's good. Yeah.
Can you hear me now? All right, have a good one.